consider the following as a measure of how strange this story is. A book was written in Egypt around 300 BCE. It is a mathematics textbook. It was still being used as a mathematics textbook, not studied as a historical curiosity, but handed to teenagers as the actual assigned coursework in British and American schools in the early 20th century. That is a working life of well over 2,000 years. Nothing else we have made does that. There is no physics text from 300 BCE in any classroom, no medical manual, no book of chemistry or astronomy or engineering. Every one of them was superseded, corrected, embarrassed, and shelved. Aristotle's physics was wrong. Ptolemy's cosmos was wrong. Galen's medicine was worse than wrong. It killed people for a millennium. Every ancient book of knowledge we read as literature or as history or as scripture. But you can hand a modern student the Elements of Euclid, and every single thing in it is still true. Not true for its time. Not a reasonable first approximation, later refined. True. The propositions Euclid proved were proved, and being proved, they stayed proved, through the fall of Alexandria and the fall of Rome, and the whole long turning of the world. And they will still be true when the last human being closes their eyes. When it was finally printed with movable type in Venice in 1482, it had already been copied by hand for 17 centuries. It has been going out to printers ever since, in more than 1,000 editions. And it is often said to have been reprinted more times than any book in the Western world except the Bible. This chapter is about how that is possible. It is about a machine that a man built out of nothing but agreements and reasoning, a machine for manufacturing permanent truth, and about the single loose bolt he left in it, which took 2,000 years to work free, and which, when it finally did, blew the roof off the universe. First, the man, who, in the by now familiar way of this book, is mostly a rumor. We believe Euclid worked in Alexandria, the brand new Greek city on the Egyptian coast, founded by Alexander the Great inherited by his general Ptolemy, who made himself pharaoh and set about buying the world's knowledge. Ptolemy built the library, and beside it the museum, the Mauseon, House of the Muses, an institution with no real precedent, paid scholars, fed and housed at state expense. Freed from any obligation except to think. It is the ancestor of every university and every research institute on the planet. Euclid was, as far as we can tell, one of its earliest stars. And that is very nearly everything. We do not know when he was born or when he died, or where he came from, or what he looked like, or whether he was cheerful or sour. Later writers were as frustrated by this as we are and did what people always do with a blank. They filled it. 2 anecdotes survive, both charming, both suspect. In the first, King Ptolemy, busy, powerful, impatient, asks whether there might be some shorter way through geometry than plowing through all these propositions, and Euclid replies that there is no royal road. It is a wonderful line. It is also told, in other sources, about an entirely different mathematician and an entirely different king, which is a reliable sign that it is a joke in search of a famous mouth to put it in. In the second, a young man who has just learned his first theorem asks what he will gain from all this, what it is good for. Euclid calls a servant in and says, "Give him a coin, since he must profit from what he learns." Also perfect. Also almost certainly invented. But notice what both stories are about, that this knowledge is not for sale, cannot be hurried, and is not useful in the way a plow is useful. Whoever made these tales up understood exactly what kind of thing had been created here, even if they were lying about the man. There is one more possibility, and I include it because it is delicious. A few scholars have wondered aloud whether Euclid was ever a single person at all, whether the name might have belonged to a group of mathematicians had Alexandria writing under a shared banner. The evidence for this is thin and most historians don't buy it. But hold the thought, because 23 chapters from now, in the middle of the 20th century, a group of brilliant young French mathematicians will invent a fictitious colleague, give him a name and a fake biography, and publish decades of work under it, deliberately, with full knowledge that they were doing to modern mathematics what someone may or may not have done at the very beginning. The subject has a long memory. Now the crucial thing, and it is the opposite of what you would expect. Euclid did not discover most of the mathematics in the Elements. Almost none of it, in fact, was his. The theory of proportion in Book 5 is generally credited to Eudoxus. Much of the work on irrational quantities traces to Theaetetus. The Pythagorean theorem was, as we have seen, old in Babylon before any Greek was literate. Geometers had been proving things for 2 centuries before Euclid picked up a pen, and earlier writers had already attempted collections like his. His achievement was not finding the facts, it was ordering them. That sounds like the work of a librarian, and I want to persuade you that it is one of the most creative acts in the history of thought. Because what Euclid did was ask a question nobody had ever pressed to the bottom. If you know a great many true things, in what order must they be arranged so that each one is fully earned by the ones before it? Think about what that demands. Take any theorem you like. To prove it, you must use other facts, and those facts must themselves be proved, using still others, and so on backwards. Every proof leans on earlier proofs. So follow the chain back, and back, and back. Where does it stop? It has to stop somewhere. If it never stops, you are in an infinite regress, and nothing is ever actually established. You are the child who answers every explanation with, "But why?" until the adult gives up. And if it curls around and bites its own tail, if A is proved from B and B is proved from A, then you have a beautiful closed loop that establishes precisely nothing, since you could build an equally beautiful loop out of nonsense. So the chain must terminate. There must be a floor. There must be some small number of things you simply accept without proof, because there is nothing underneath them to prove them with. This is the great, uncomfortable, permanent truth about knowledge, and Euclid faced it more squarely than anyone had before. You cannot prove everything. You must begin by assuming something. The only question is whether you are honest about what. That is the whole idea of an axiom. Not a truth so obvious it needs no proof. That is the schoolroom version, and it is misleading. An axiom is a declared starting point. It is a mathematician putting his cards face up on the table and saying, "Here is exactly what I am taking for granted, all of it, nothing hidden up my sleeve. From here on, I will prove everything else. And if you dislike my conclusions, you must argue with these, because there is nothing else to argue with." There is a kind of intellectual courage in this that I find genuinely moving. Every other system of authority in the ancient world, every priesthood, every court, every school of philosophy, worked by concealing its foundations, by making its first principles feel too sacred, are too obvious to examine. Euclid does the reverse. He walks to the front of the room, lists his assumptions on the board where anyone can attack them, and then never uses anything else for the rest of the book. So, what did he ask for? Book I opens with 23 definitions, in which Euclid tries to pin down the words he's about to use, point, line, surface, circle, and the rest. Then he asks for 2 small sets of gifts. The first he calls common notions, general rules of reasoning, not specifically about geometry. Things equal to the same thing are equal to each other. Add equals to equals, and the results are equal. The whole is greater than the part. These are the grammar of argument itself. The second set are the postulates, the properly geometric assumptions, and the heart of the thing. There are 5, and the first 4 are so brief you could carve them on a coin. You can draw a straight line from any point to any other point. You can extend a straight line as far as you like. You can draw a circle with any center and any radius. All right angles are equal to one another. Look at what the first 3 actually are. They are not statements about the world. They are permissions, a description of what you are allowed to do. And what you are allowed to do is connect 2 points with a line, extend a line, and draw a circle. Which is to say, precisely and exactly, the 2 physical instruments sitting in every geometry set ever sold, a straight edge and a compass. That is why, for the next 2,000 years, straight edge and compass was not one method among many for doing geometry. It was the definition of a legitimate construction. Those 2 humble tools are not equipment. They are Euclid's axioms made out of wood and brass. And the reason certain famous problems, squaring the circle, trisecting an angle, tormented mathematicians for millennia is that they were asking whether a particular result could be squeezed out of exactly these permissions and no others. The answers, when they finally came in the 19th century, were all no. Impossibility again? It keeps happening. Then comes the 5th postulate. And you do not need to be a mathematician to feel that something has gone wrong, because you can simply look at it. Where the first four are one-line requests, the fifth is a mouthful of a paragraph, dense with conditions. That has to be read twice. If a straight line falls across two other straight lines, and the two interior angles on one side of it add up to less than two right angles, then those two lines, if you extend them far enough, will eventually meet on that side. Read it again. It is not wrong. It is not even hard once you draw the picture. If two roads lean toward each other even slightly, then keep going, and they will cross. Obvious enough, but it does not sound like the others. The first four are things you can check in a heartbeat, on a page, right in front of you. The fifth makes a claim about what happens out at the far end of two lines, extended indefinitely. Off the page, past the edge of the desk, out past the room and the city and the horizon, in a place no one has ever been. It asks you to accept something about infinity. And here is the detail that tells you Euclid knew. He avoided using it. Having stated all 5 postulates up front, he then proceeds through his first 28 propositions, an enormous stretch of geometry, including a great deal that you would swear needed it, without invoking the fifth at all. He gets everything he possibly can out of the other 4 first. Only at proposition 29, having exhausted every alternative, does he finally reach for the awkward tool he wishes he did not need. That is not the behavior of a man comfortable with his assumptions. That is a man holding his nose. Remember this? It is the loose bolt. Now watch the machine start. Proposition 1 of Book 1 asks for something modest. Given a straight line, build an equilateral triangle on it, a triangle with all 3 sides the same length. Here is the construction, and it is so simple you can do it on a napkin. Take your line segment. Put your compass point on one end, open it to the other end, and draw a circle. Now put the compass point on the other end, same opening, and draw a second circle. The 2 circles cross. From that crossing point, draw a line to each end of the original segment. Done. And it must be equilateral, because the 2 new sides are radii of circles whose radius was the original line. So all 3 are the same length, necessarily, by the very definition of a circle. Not approximately. Not as far as anyone can measure. Necessarily. Look at what that used. Postulate 3, to draw the circles. Postulate 1, to draw the connecting lines. A common notion, to conclude that things equal to the same thing are equal to each other. That is all. Nothing else exists yet, and nothing else was needed. And now proposition 1 is in the bank. It has been earned. From here on, Euclid may use it whenever he likes, and so may you forever, without reopening the question, because it has been settled, permanently, and settled things stay settled. Proposition 2 may lean on Proposition 1. Proposition 3 may lean on either. The permissions accumulate. Each new result is a new tool in the box, and the box only ever gets fuller. This is the machine, and it is a ratchet. It turns one way. Some 460-odd propositions across 13 books, each one clicked into place on top of the ones below, and nothing anywhere in that vast structure resting on anything but the 23 definitions, 5 common notions, and 5 postulates declared on the first 2 pages. 46 propositions later, the ratchet arrives at Book 1, Proposition 47. It is the Pythagorean theorem. And I want you to feel the weight of that, because we have been walking toward it since Chapter 2. Babylonian scribes knew this relationship 1,000 years before Pythagoras, and used it, and built tables of it, and taught it to their students, and never once, on any tablet we have ever dug out of the sand, said why. They had the phenomenon. They skipped the reason. Here, at last, in a book written in Alexandria, the debt is finally paid. A diagram of 3 squares hanging off a triangle, a dozen lines of argument, and the thing is not merely known but understood, established for every right triangle that has ever existed or ever will. In this universe or any other where the postulates hold. The medieval students who had to fight their way through it, and often lost, gave the diagram grim little nicknames: the windmill, the bride's chair, the peacock's tail. It was the wall you hit. Somewhere in the Middle Ages, it acquired the name Pons Asinorum, the bridge of asses, though that title properly belongs to an earlier proposition, the 5th. The first place in the book where a real number of students simply could not get across. The bridge of asses is, I think, an underrated compliment to the human race. It is the point at which a 15-year-old discovers that they are being asked not to remember something but to follow something, and that no amount of trust in the teacher will get them over, because the crossing has to happen inside their own head. Nobody can do it for you. That is what the machine demands. The 13 books are not a random pile, and their shape tells a story. Books 1 through 4 do plane geometry, triangles, parallels, circles, the constructible polygons. Book 5 is the strange, difficult, magnificent one, and it exists because of Chapter 3. Remember the wreckage. The diagonal of the square could not be expressed as a ratio of whole numbers, and Greek mathematics had lost its nerve about number altogether. But you cannot do geometry without comparing sizes. This is to that as that is to the other, and if some lengths have no numerical ratio, how can you compare anything safely? The answer, credited to Eudoxus and preserved here, is one of the cleverest ideas in ancient thought. Since you cannot say what the ratio of two lengths is, don't try. Instead, compare two ratios by testing them against every possible whole number multiple. Take any two whole numbers you like, use them to scale up both pairs, and see which scaled quantity comes out bigger. If the two ratios behave identically under every such test, for all whole numbers, without exception, declare them equal. It is a definition built entirely out of infinitely many comparisons, none of which requires naming the unnameable. It let Greek geometry work with incommensurable magnitudes for 2,000 years without ever admitting they were numbers. And when 19th century mathematicians finally sat down to build the real numbers properly from scratch, Chapter 19, they would reach for an idea so close to this one that Dedekind himself acknowledged the debt. The workaround outlived the emergency by 22 centuries. Books 7 through 9 turn to numbers proper, and hidden in Book 9, as Proposition 20, is a jewel, the proof that the prime numbers never run out. You can hold this one in your head. Primes are the numbers divisible only by themselves, and 1, 2, 3, 5, 7, 11, 13, the atoms out of which every other number is built by multiplication. As you walk out along the number line, they get scarcer, and it is entirely reasonable to wonder whether eventually they stop. Euclid proves they don't, using the same reversed weapon we met in Chapter 3. Assume they do. Suppose there were only finitely many primes. Then you could list them all. Multiply every prime on that list together and add 1. Now look at the enormous number you have just made. It cannot be divisible by any prime on the list. Divide by any of them, and you are left with a remainder of 1 every time by construction. So either this new number is itself prime, or it's divisible by some prime that is not on your list. Either way, there is a prime you missed. But your list was supposed to be complete. Contradiction. The list can never be complete. There are infinitely many primes, and that is the end of the matter, forever, from 6 lines of reasoning that a child can follow. The last book, Book 13, is the summit the whole structure has been climbing toward. It concerns the 5 Platonic solids, the tetrahedron, cube, octahedron, dodecahedron, icosahedron, the only solids you can build from identical regular faces meeting identically at every corner. Euclid constructs each one. And then he closes the Elements and 13 books of accumulated machinery by proving that there are no others. Not no others have been found. No others can exist. 5, and only 5, in this universe and any other. It is a proof of impossibility, standing as the final chord of the greatest textbook ever written. And it is, quietly, exactly the kind of result this whole book is about. The Greeks had learned to do something that no amount of measuring, checking, or looking will ever do, to close a door and prove it cannot be opened. Before we come to the loose bolt, let me say plainly what the machine gave us, because it escaped mathematics almost immediately, and it is loose in your life right now. A proof is an argument that does not require you to trust the person making it. That is the revolution. Every other way of settling a question in 300 BCE, and mostly today, runs on authority. Someone credentialed, powerful, holy, or persuasive tells you a thing, and you weigh how much you believe them. A proof cuts the person out. Euclid could be a liar, a fool, a committee, or a fiction. It does not matter in the slightest. The argument is on the page. Check it yourself. If each step follows, the conclusion holds, and Euclid's character is as irrelevant as the color of the ink. Everyone who encountered this felt its force, and a startling number tried to borrow it. Spinoza wrote his masterwork of philosophy in geometrical order, with definitions and axioms and propositions, trying to prove ethics the way Euclid proved triangles. Newton, who could have written the Principia in his own calculus, chose instead to cast the physics of the universe in classical geometric proofs, because that was what an argument was supposed to look like. And when Jefferson's committee needed to found a country on something firmer than the will of a king, they reached, whether consciously or not, for exactly Euclid's opening move. We hold these truths to be self-evident. That is an axiom list. That is a nation declaring its postulates on the first page and proposing to derive the rest. My favorite case is Abraham Lincoln. As a young lawyer, he kept finding the word demonstrate in arguments and realized he did not truly know what it meant, not make plausible, something stronger. So he bought the Elements, took it home, and by his own account, worked through the first 6 books by lamplight until he understood what it was to prove a thing. He was still carrying that book in his saddlebags on the circuit years later. There is a straight line, and not a long one, from a geometry text written in Alexandria to the man standing at Gettysburg, opening with the proposition, all men are created equal, and speaking of a nation dedicated to it. The way a mathematician is dedicated to an axiom. And now, the bolt. Almost from the beginning, readers came back to that 5th postulate and felt the same itch Euclid clearly felt. It was too long, too complicated, too much of a claim. It looked, everybody agreed, less like an assumption than like a theorem that had somehow escaped the building without being proved. So they set out to prove it. If you could derive the 5th postulate from the other 4, you would have tidied the greatest book in mathematics, trimmed its foundations from 5 assumptions to 4, made the perfect thing more perfect. They tried for 2,000 years. The Greek commentator Proclus tried and produced an argument that turns out to smuggle in the very thing it is proving. Mathematicians across the Islamic world took it up with enormous ingenuity. Ibn al-Haytham, Omar Khayyam, Nasir al-Din al-Tusi, and each of them got somewhere. And each of them, somewhere in the machinery, quietly assumed something equivalent to the postulate itself. It kept happening. It kept happening in disguises. Someone would prove the 5th postulate from the innocent-sounding assumption that there exist 2 triangles of the same shape and different sizes, or that any 3 points not in a line lie on some circle, or that the angles of a triangle add to a straight angle. Every one of those turns out to be the 5th postulate wearing a hat. The strangest attempt of all came in 1733, from an Italian Jesuit named Giovanni Saccheri, who published a book with the triumphant title Euclid Freed of Every Flaw. His plan was the one we have used twice already. Assume the postulate is false and derive a contradiction. So he assumed it and started working, and out came a strange, alien geometry, theorem after theorem, weird and beautiful, and entirely free of contradiction. He kept going. He got further into it than anyone in history. And then, unable to find the collapse he needed, he wrote that these results were repugnant to the nature of the straight line, declared victory, and died the same year. He had it in his hands. He had walked into an entirely new universe, taken careful notes on its geography, and refused, at the last, to believe he was standing anywhere at all. It would take another century and 3 people working independently and mostly in obscurity, before anyone was willing to say the thing out loud. That the 5th postulate cannot be proved from the other 4, that Euclid was right to state it and right to be uneasy, and that the other geometry, the repugnant one, is perfectly consistent. Not a mistake. A choice. 2,000 years of failure was not incompetence. It was people trying to prove something that was never a theorem in the first place. And when that finally happened, in the 19th century, geometry stopped being the description of space and became one of several. Which sounds like a technicality, until a patent clerk in Bern went looking for the mathematics to describe gravity and found, waiting for him, a geometry built by men who thought they were only playing. That is chapter 17, and I will not spend it here. For now, hold the picture. A fortress of reasoning, the most durable thing our species has built, standing for 20 centuries on 5 plain sentences, with a hairline crack running through the 5th, put there by the architect himself, who saw it, and could not fix it, and was honest enough to leave it showing. Euclid was also, we should admit, not quite as flawless as his reputation. Modern eyes find gaps. In Proposition 1, the very first thing he proves, he assumes those 2 circles cross, and nothing in his postulates actually guarantees it. It is obvious in the diagram, which is precisely the problem, because the whole point of the machine was to stop trusting diagrams. When David Hilbert rebuilt the foundations of geometry properly in 1899, he needed about 20 axioms to do what Euclid had done with 10. Mostly to nail down the things Euclid's I had simply taken for granted. But this is criticism of the kind you can only make from inside a building somebody else built. Euclid invented the standard by which Euclid falls short. That is the highest compliment available. The machine was now running, and Alexandria was full of people who knew how to use it. One of them was a young man who came to study there and then went home to Syracuse, in Sicily, home to a city he would defend, in old age, with weapons of his own design, against the greatest army in the world. He would take Euclid's rigid, careful, finite methods and aim them at the one thing the Greeks feared most, the infinite. He would slice curved shapes into infinitely many pieces and get exact answers. He would come within a hair's breadth of inventing calculus 19 centuries early, and then die with a Roman sword in his side and a diagram in the sand. He is the greatest mathematician of the ancient world, and he is next.